feel a bit underprepared. I don't have a video to show you. Good afternoon. My name is Lutz Martin. I'm the president of the Philological Society. Memory, where there is a bit of about her life and testimonials of people who knew her and wrote about her. So do have a look at that. And the other reason is if you're not a member of the society, please join the society, and you can do that on the website as well. And it has lots of advantages and very little drawbacks, so please do that. Today I'm very pleased to introduce this lecture by Mark Steedman, who talks about natural language and artificial intelligence, a huge, super topical topic. I'm really excited about that. I've known Mark for a long time and his work for a long time, in particular on categorical grammar. When I came to this country in the 1990s, I was working with another colleague of ours, Ruth Kempson, on dynamic syntax, and we looked at Mark's work always with great interest and admiration and inspiration. And before Mark talks, he will be introduced by another dear friend of college, Shalom Lappin. Now, Shalom, when I came to the UK and did my master's at SOAS, he was my first teacher of semantics. And there's lots of memories I still have from that time, and lots of consequences coming out of that. After the talk, there will be room for discussion, and there will also be a drinks reception, to which you're all very much invited. Let me hand over to Shalom now to introduce Mark, and then come to the main point of the afternoon. Thank you, Shalom.
Thank you very much, Lutz. It's a great honor and a pleasure to introduce Mark Steedman. I've known Mark for close to 40 years. We were reminiscing recently in the Fellows Room. We first met in 1989 when he was at the University of Pennsylvania and I was at IBM Research in New York. He came back to Edinburgh and I followed to London a few years later. Mark's work is very important and seminal at the intersection of linguistics and computer science. He is best known, as Lutz has mentioned, for his work on CCG, combinatorial categorical grammar, which is one of the most articulated and effective frameworks for both linguistic analysis of theoretical interest, but also for a variety of computational applications, in particular rapid accurate parsing. He has also worked in areas adjacent to linguistics, like the application of computational modeling to music, and of course to general questions of the relationship between natural language and AI. He's had a very significant impact on my work, and I'm very pleased and proud to think of him as a colleague and a friend. I'd like to call on Mark now to give his talk.
Thank you for that kind introduction, and thank you for the invitation. It's a great honor to give the Anna Morpurgo Davis lecture. The title has switched around for reasons of prosody, but I kept this slide in the deck in order to draw your attention to the fact that I'm going to talk about, particularly in the second part of the lecture, talk about the work of my students, and in particular the students who are mentioned on this slide here. Here they are. These are the people who actually did the work. Here's my talk. So I want to talk about, or I've been asked to talk about, the relevance of large language models and machine learning in general and artificial intelligence to the disciplines of linguistics, psychology, and the philosophy of language. And in these studies, two components have traditionally been distinguished. And each of those constituencies tends to forget about the concerns of the other component. But the two components are the grammar, which is symbolic and logical. It has a semantics. And its purpose is to support semantic interpretation. But there's also a component that I'm going to call the model. I'm going to talk about large language models as an instance of the model, which is also recognized by psychologists as a probabilistic mechanism which assigns measures of similarity between terms and phrases. And it's based on similarity of association between those tokens or symbols and sequences. The purpose of the grammar is to support understanding and inference, and the purpose of the model is to limit the complexity of mapping strings to meanings, because for one reason and another, and I don't have time to go into the interesting question of why this is, human grammars tolerate a great deal of ambiguity. And one of the main purposes of the model is to reduce that ambiguity and reduce the problem of search so that you can find your way to the meaning that is intended. This traditional view of language as having these two components that I'm going to refer to just loosely as the grammar, including the semantics, and the model, is reminiscent of a distinction that's recently been brought to attention among psychologists by Kahneman. So Kahneman distinguishes between two kinds of system, which he calls System 2 and System 1. System 2 is a high precision but slow, and I'm going to define precision in a moment, but it's a high precision but slow symbolic system which continually interacts with Kahneman's System 1, which is a high recall, fast, sloppy, and imprecise, but often good enough system. And very commonly, the computer scientists among us implement that as a finite state machine, because finite state machines have extremely nice properties for in computational terms. Precision, when I talk about precision, I'm going to use the terms precision and recall in this talk to distinguish those systems. High precision means giving a low proportion of false positive, incorrect answers. Recall means finding a high proportion of the positive answers, the correct answers, but you can have high recall and be imprecise if you provide not only high recall of the correct things, but some false positives. An example of an organism that I have worked with myself in the early days of my career is pigeons. Pigeons are essentially a System 1 animal. And large language models, I'm going to argue, are System 1 on steroids. Just very large pigeons. But very interesting pigeons. It's really insulting to refer to large language models in the same phrase as pigeons. All of us the psychologists and the linguists on one hand, and actually the computer scientists on the other hand, have been surprised by the performance of large language models. It's absolutely amazing what you can do with these things. The surprise of large language models for the linguists and philosophers, less so for the psychologists who are used to working with pigeons, is just how much can be done by system one alone, the model alone, especially when the model is as large and trained on the amount of data that large language models are trained on. These things do remarkable things that you wouldn't expect from merely being trained on large amounts of text. They are very good at answering linguist questions concerning grammaticality judgments. So if you offer a large language model a sentence which violates the fixed subject constraint, it doesn't matter what that is, the large language model will say it's not a very good sentence. And if you ask it what would make it better, it'll say, well, it would be better if you left the that out. Those of you who know this phenomenon, I don't have time to go into it, will know what I'm talking about. They also write pretty good computer code, usually draft computer code that you really have to check because it might contain false information. And it might be written in a rather odd style, a rather old-fashioned style because of the data that it's been trained on and the rapid development of the field. Nevertheless, it can speed up the productivity of human coders very greatly indeed. Now, among these abilities is just simply answering questions. So if you start searching on the internet for the answer to a question, you will automatically get a Gemini summary of what it's found in answer to your question, and it's very often a very good answer to the question. While it is an interesting possibility that large language model training works by inducing the mechanism that we ourselves use to do these tasks, whether it's answering questions, making grammaticality judgments, or producing computer code, it's an interesting possibility that the large language model actually works the way that we do by inducing a mechanism of that kind. I actually personally think that that is very unlikely to be the case. I think that's not the case. I'm going to instead argue that large language models do these tricks on the basis of very high-order latent Markov models. The mechanism that Chomsky famously said was not capable of expressing the details of human language, or a theory of human language in any case. And I'm going to say that what they're doing is covering very large string sets of the kind of text that human beings actually produce, and even the code that they actually produce for designated purposes. It's important that you should know that the modern large models are trained not only on text information, but also on code. They scrape all the code on GitHub, and the code on GitHub has large amounts of commentary and that say what it's for, and it has large amounts of history of the development of the code. So this is very helpful information for them to be trained on. In fact, many tasks that human beings find extremely hard and have to spend years learning actually come down to assembling sequences of known elements, and very often sequences that have actually been constructed by somebody else before. So although human language is unboundedly productive, most of what you hear is the same thing over and over again. And these tasks that human beings find hard include game playing. Playing chess is hard for human beings, but it's still sequencing known units. And a great deal of computer programming, I can tell you from experience, is putting together units that you have very painfully learned are going to do the kind of things that you want. The surprise for the computer scientists of what I've called the unreasonable effectiveness of the model. There's an early paper talking about the unreasonable effectiveness of mathematics in the sciences. And this is the same kind of effect. It's an effect that you wouldn't necessarily expect from the nature of mathematics or large language models. The surprise for the computer science guys is that the model that is System 1 can't do everything that System 2 can. In particular, despite these reports of stunning success in coding and mathematical theorem proving, the ability of large language models to do logical inference, my talk is essentially going to be about logical inference. The ability of large language models to do inference is surprisingly limited. I'm going to say that it's quite specifically limited in ways that lead to generation of dismayingly convincing false positives. So they give you answers to questions that sound as though they might be true, but you should always check the truth of those generations. And they're called hallucinations, but they were also what I referred to earlier as a lack of precision in answering. They are also limited in their ability to generalize beyond the training data. So there are, when you train, I won't go into the detail, I don't have time. What I'm going to argue is that large language models are really good at phenomenal recall of incredible quantities of relevant sequential data. Now, they're not just memorizing the training data, they're organizing it in a way that allows them to come up with relevant material for the purpose of what you need. So I said I was going to talk about inference. So I need to spend a little bit of time making the point that human discourse, including answering questions, always involves an element of inference. And I want to give you a toy example of this influence at work. This is not an example that a large language model will have any difficulty with whatsoever. They'll do very well. If you type it in on your phone right now, they'll do very well on it because it's such a simple example. But this is just to make the point that inference is involved in question answering. So you want to know who played against Manchester United last night. And the text, in other words, your newspaper or maybe a collection of newspapers or a collection of documents that you find on the web, says things like Arsenal beat Manchester United, Manchester United's defeat by Arsenal, Arsenal obliterated Manchester United, etc., etc. There are many ways of answering your question. In fact, there are too many ways of answering a question for exact match to the text that you find in your newspaper on the web to actually give you the answer. What you need to do is to do a tiny bit of inference to get from text like those 3 bullets there to the answer to your question, that it's Arsenal who played Manchester whenever it was. So we need inference. Can large language models do inference? The question, can large language models do X, is always the wrong question, and it's not the question that I'm going to discuss today. In fact, I'm going to, since large language models are continually getting larger, it's a moving target to say exactly which examples a large language model will be able to do and won't be able to do. The right question is always, when a large language model is claimed to do X, what is the large language model actually doing? And my whole talk is going to be about what the large language model is actually doing and how we can make the most of large language models from what it's actually doing. And again, I'm going to say that large language models are essentially encoding serial pre-training data, serial computer programs, serial text, didactic text, and they're doing a very marvelous trick that I think everybody was just surprised that this is what they were doing. They're indexing that text by associative similarity. In other words, if you present the model with some kind of text or some kind of code, it will find its way to things that are similar in the context that you have presented your example. And this is a marvelous trick that is responsible for everything that they do. The large language models encode. I want to make a point about that, indexing things by similarity, associative similarity. Similarity is a symmetric relation. If P is similar to Q, then Q is similar to P. But inference, this makes it quite unlikely a priori that large language models are going to be able to truly do logical inference. Because entailment, for instance, in that earlier example, from a team beating another team to a team playing against that team, is non-symmetric. It doesn't follow that if you played against somebody, you beat them. And what that tells us is that the large language model must be doing something else. So let's think about what we should think about when we talk about a large language model. You can think of a large language model as a sphere. It's a hypersphere, so it has hundreds of dimensions. But it's compressed down from a much larger dimensional space, a space of essentially with as many dimensions as you have words in your vocabulary, on the basis of keeping the what's called the Euclidean distance in this sphere, keeping the triangle inequalities in that Euclidean space, preserving those inequalities. And what that has the effect of doing is compressing these many dimensions into a smaller number of dimensions of similarity. So you can think of this as a sphere, a hypersphere, on the dimensions of which there are sorts of similarity, dimensions of similarity. And the important thing about this hypersphere, and the thing that I want you to hold on to, is that there is known to be a gradient of generality from the center of that hypersphere to the periphery of the hypersphere. So very general terms on any dimension of similarity tend to be at the center of the hypersphere, and specialized terms are on the outside. So the term dog is further towards the center of the hypersphere than the word dachshund, because dachshund is a more specialized term along the dog dimension. And it'll also be important to remember that terms that stand in the relation of a generalization, dog is a generalization of dachshund, are also in the terms the other thing to know about that dimension is that the term dog, the general term, is more frequent than the specialized term dachshund. So there's a dimension of generality from the center of this space to the periphery, and also a generality of frequency from the center to the periphery. And that's going to be an important thing for us to understand. And it's going to be important to remember that terms that stand in the relation of a generalization, dachshund to dog, are also define a notion of entailment. So if you're a dachshund, you're a dog. But it doesn't follow, if you're a dog, it doesn't follow that you're a dachshund. So that's the only technical information that I'm going to give about how these things actually work. So how are we going to get inference done in order to do question answering? There are two possible ways that I want to talk about. You can actually you can regard the large language model as being itself a latent entailment model, that it will actually tell you that if you're a dachshund, you're a dog, and won't tell you that if you're a dog, you're a dachshund. And we can exploit this, if that's the case, if it's legitimate to regard large language models as being latent entailment models, we can actually manipulate the large language model in the way that all the can you tell me something about the time? Well, that's what I don't know how to understand. Okay, so, sorry? Yeah, but that's going to be too late. So we can regard the large language models as being a latent entailment model. We can just say, although it's indexing everything by similarity, maybe it'll do entailment. The other thing we can do is use some logic. We can induce an entailment graph. And by the way, when I'm talking about entailment, I'm not talking about the logician's sense of entailment. I'm just talking about probabilistic implicature. We can induce a graph of entailments, for instance, between beating and playing against, and we can use that to answer questions. And the way you do this is to get a large amount of multiply authored text about the same events. In other words, newspaper text, news text. And we can parse that text with CCG parsers or something like that. Actually, any old bag of nails will do. And we can find out that if you read in one news story that, for instance, a company bought a company, you're likely to read in another one that the company owns a company. But of course, it's not going to work the other way around. You're going to find lots of statements about companies owning things. When they didn't buy them, they developed them themselves. So I want to compare these two ways of doing the kind of inference that I've said is necessary for reading in text, for answering questions about text.
15 minutes left. 15.
Okay, so the large language models, I'm going to argue, and the entailment graph, the one that actually tells you that buying entails owning but not the other way around, they have opposite qualities. So the large language model is high recall but low precision. So I've said it's prone to hallucination. It gives you false positive answers. The entailment graph is high precision but low recall. We can't parse anything like the trillions of words that large language models can memorize or more strictly speaking, encode. So this complementarity, I'm going to argue, calls for hybrid models. What we want is to use the large language model, we use the entailment graph, the logical mechanism, for its precision, but where its precision, where it's too slow or too sparse, we want to use the large language model as to get some recall. And the question is, can we get the recall without corrupting the precision of the logical mechanism? So, are large language models latent entailment models? Well, we did a lot of work on entailment graphs, but then the large language models came along, and our papers started getting rejected with the reviewer comment, "Why didn't you just ask GPT?" So we had to do a lot of work that I'm describing in this talk, finding out exactly what large language models were doing. My students, whose work I'm describing now, showed that the performance on natural language inference data sets by large language models is dominated by two biases. There's an attestation bias that if the question is there in the training text, then the large language model is extremely likely to just answer that the answer to that question is true. The other bias is relative frequency. So if the entities that you're talking about and the relation you're talking about, for instance, if your question is, who owns YouTube? And the text says Google bought YouTube. If it's true that Google owns YouTube, you tend to answer yes regardless of what the text says. Or the large language model tends to answer yes. And if the entities, namely Google and YouTube, are frequent, it also is biased towards giving a false positive answer or a positive answer. And this means that performance degrades for test items that are adversarial to these two biases. This is a crippling disadvantage or feature of the large language model, because these biases are seen across all language models, open, closed, it doesn't matter. And they are in fact inherent in text and the embedding algorithms that are used to compress that hypersphere that I talked about. And the biases are even seen in the test sets. The test sets are actually biased towards questions to which those biases tend to give a correct answer. And this means that we're wildly overestimating in the computer science literature, the computational linguistics literature, we're overestimating the extent to which these models are actually doing inference. So here's just a quick example. The top example, if the question is, does the ash contain iron? And the text says the ash is rich with iron, which is an entailing example. You should answer yes to this question. The frequency bias is that contains is actually more frequent than is rich with, and so the bias tends to favor answering correctly, actually, yes, it's entailing. But if you take the second example, the statement about traveling to, the relation traveling to is less frequent than the relation reached. I actually found this surprising, but that's what is actually the case. So if asked whether John reached Paris entails that John traveled to Paris, which is entailing, the bias is the wrong way around. Okay, I'm going to skip this slide in reasons of time, but when we compare the performance of the large language model on the bias-consistent examples, it does much better than its performance on the bias and adversarial examples. So what you see, I don't have time to go through the detail, but what you see is a massive drop from test examples which are consistent to test examples which are adversarial to these biases. And the bias is greatest in the case of GPT, which is the closed model, which means that GPT has been doing some extra training to exacerbate these biases. So to summarize this section, the use of very large language models as latent entailment models, just using them out of the box, is unsafe for answers, for cases where it matters if you get a false positive answer. So cases, there are lots of tasks where all that matters is recall. This famous example of the latest model from Anthropic being excellent at finding security bugs in the operating systems that we all use when we use computers. That's a case of an example, a task where all you care about is recall. You want to get lots and lots of security weaknesses, and you don't mind if there's a few false positives, because you will actually find that those aren't in fact things that you need to worry about. But tasks like medical advising, financial advising, these are cases where a false positive can be a real disaster. So if that's the nature of your task, then using large language models as latent entailment models, and therefore as for question answering, is likely to be unsound. So I want to say a little bit about our work with entailment graphs. I sort of told you how you build them. You look for coincidences in text about the same events, where if a company is talked of as buying another company, some other text talks about that company owning that company. And you work out from that, using statistics, of course, you work out an entailment graph that has the nodes are relations like buying and owning, and the arcs are directional arcs, which say that that entailment holds. So you can use that thing in question answering. And this process is completely unsupervised, so it's likely to have fewer biases than the large language models. I'm going to skip over this slide, except to say that at the bottom it says that entails is used in this probabilistic sense rather than the logician's sense. We've done that. We've built entailment graphs that, for English and Chinese, it took us 3 years to build a strong graph for English and to find out how to do this. But once we'd done it, the method scaled. So we practiced on 20 million sentences, but we can immediately scale to 200 million sentences and keep on with that. English took us 3 years to develop, but Chinese, we just had a pipeline that we could feed Chinese text through. I don't even speak Chinese, but fortunately the students I mentioned do. We did that in 6 months and got a stronger graph for Chinese than for English. And in fact, if you put the two graphs together, you get an even stronger graph, because Chinese news text talks about different things from English news text. So here's the second summary, which is that entailment graphs can be used in question answering for bridging inference from text or knowledge graphs, which are databases essentially, to the question in the task with high precision. So this is a method that actually finds genuine entailments. Those of you who are linguists will notice that I haven't sort of said that the buy-own relation actually depends on temporality. If there's another event if there's an event of selling, then that's something to worry about. But I'm going to gloss over those details and say that these things are fine. The weakness marked by this dangerous bend sign hasn't quite come out in the translation to PowerPoint, but the weakness of entailment graphs is sparsity. You can't read enough text. There's a thing called Zipf's law, which says that for anything you're interested in language, like rules of syntax, there are a lot of rules of syntax, but about 4 of them do all of the work, do 90% of the work in data sets like the Penn Tree Bank. And that means that just going up by an order of magnitude in the amount of text that you parse just gives you better counts on things that you've already seen before. It doesn't give you many new relations. And so the question is, that I mentioned earlier is, can we use large language models to compensate for sparsity in the entailment graph? I'm going to talk about two ways. Well, I'm just going to talk about two ways of doing this. One of them is to kind of chain down the large language model. So if the entailment graph answers the question, buying entails owning, then you should just settle for that. But suppose that the buying term is some rare word, perhaps purchase is rarer than buying, and you didn't read enough text to work out that purchase entails buy, as well as buy entails own. What you should do is you should look in the large language models for the large language model representation of purchase. Look for nearest neighbors of that in the large language model, such as buy, that are actually in the entailment graph. And if you can find that, just assume that purchase entails buy because it's a near neighbor, and let the entailment graph do the rest of the work. And that is a very strong technique. I'll show you, I'll just skip to the results. If you do that with the black dotted line is the entailment graph on its own. But it's called smoothing. If you smooth the entailment graph with the large language model in the way I've described, you get the green line above the blue line. This is a precision recall graph, and across the entire range of precision and recall, the green line is, for working purposes, is above the black line. If you do this, this is smoothing the premise. If you smooth the hypothesis, the question that you started with, you look for near neighbors of the question in the large language model, then you do exactly the same amount of damage. That's actually destructive. And the magenta line is below the black line. It's strikingly, pretty much as much below, if you smooth the hypothesis, the question, as if you smooth the premise, the thing in the text. Why is that? Well, it's because I need to say something before I get to this slide. It's because of that generality and frequency gradient. If you're looking for a nearest neighbor of purchase, the rare word, that is in the entailment graph, buy, then you're going from a specialized term, a rare term, a low frequency term, to a higher frequency term and a more general term. And more general terms are entailed by more specialized terms. Hypernyms are entailed by hyponyms. And that's why it works. But of course, if you do it on the other end, on the hypothesis end, the question end, you're going in the wrong direction. It actually makes things worse. So what we're doing here is we're exploiting the frequency gradient and generality gradient that is inherent in the way the large language model was built. And we're only doing it when we have to. And by and large, we're winning on it. Of course, that's only in a statistical sense. It's gone orange. Okay, there is one or 2 minutes, I'm sure. Yeah, there is one more technique that I'm going to briefly talk about, which is to use the attestation bias in the large language model as representing true facts. It's biased towards things that are said in the training text, which tend to be true facts, or at least things that somebody thought were going to be true. And so if you find a connection to those, if you find entailments on that basis, you're on a sound, that's the way the original entailment graph worked. So what we do is we take an entailment like Peary reached the North Pole. Does that entail the North Pole was discovered by Peary? It does not. We get the large language model to give us statements like Peary reached the North Pole, person reached a location, and it comes up with Christopher Columbus reached the Americas, because that's true. Neil Armstrong reached the moon, because that's true as well. And then we ask it questions. We ask it whether the corresponding answer, the Americas were discovered by Christopher Columbus, the moon was discovered by Neil Armstrong. We ask it whether those are true. And then we do the statistics that we did on the entailment graph to decide whether to believe that this is an entailment or not. So since these largely come out as being, it says no, Christopher Columbus didn't discover the Americas, it gets a correct entailment. So here's my concluding slides. Large language models can do very many surprising, delightful, and useful things. They do so on the basis of a content-addressable encoding of all the text, all the code that they've been trained on, in a way that is quite unlike humans doing similar tasks. I believe, therefore, that there is a great future for hybrid systems combining System 2, the thing that linguists and psychologists are interested in, and a neural computational System 1 of the kind that is represented by large language models. And to make it happen, and I'm going to close with one further remark, it's going to be necessary to extend both System 2 grammar and System 1, the model, to modalities other than language and to action in the world. And this is going to be hard. Large vision models built by the same techniques as the large language models do not currently work well at all. They don't generalize in the same way, and they don't even get better the larger they are in the way that large language models so impressively do. And if you ask why this is, it's something to do with language. It's to do with the fact that language models are based on modeling sequences of words, and words really are general purpose. They apply to all sorts of situations. If you look at what the vision modelers are doing, they're using tokens, entities like pixels. Pixels don't have a semantics. The fact that this pixel is brown doesn't tell you anything general about the situation. So I'll close at that point saying that I believe that image tokenization is the most important open problem in System 1, large models of all kinds. Thank you.
Just indicate with your hand. Steve, yes. That was fast.
I'd like to ask about creativity. I'd like to ask about creativity. One of the questions that people have asked about large language models is, are they creative in the more or less in the Chomskyan sense? And we'd all think no. You know, they're System 1. They're just stochastic objects. But very recently, they've been finding proofs of open mathematical questions which mathematicians are astonished by. And on most counts, they would count as instances of creativity.
Yes. Is this thing on? Yes. So I have two things to say about that. One is that if you examine the instances, even Donald Knuth's recent example of genuine help given by a model in solving an open mathematical problem. There's a danger of what I call the ELIZA effect. The very first conversational computer was just a tiny, tiny finite state machine that used a few sort of pattern-directed moves in conversation, and it immediately convinced naive users that it was actually conducting a conversation. And I think that we have to be, even now, we have to be very careful of ELIZA effects, that we're unable to resist interpreting the output of large language models and models of all kinds as having the same kind of calculation, the same kind of computation behind it as we do ourselves. The thing that Chomsky didn't know when he made his claims about the capacity of finite state machines, and these are finite state machines, is that Chomsky and Shannon could not imagine finite state machines of the gigantic order that we're dealing with now. I don't even know how to put a number to the order of Markov process we're dealing with now. And if you have an unbounded order Markov model, you can cover any string set, any sequence of moves in a game, or even sequences in a proof that a human being is capable of doing. And this is why large language models are astonishingly fluent. They never make grammatical errors, except ones of the kind that human beings make themselves and are there in the training data. I think that there are still limits on creativity in the technical sense in what these things can do, but nobody ever made any money by betting against a large language model on a particular example, because the bigger they get, the better they do. So I think I'm going on too long, so I think I'll say, I think a lot of caution is in order in interpreting those results.
Yes, David, and after.
Thanks a lot, Mark. I heard a thing the other day where a lot of the UK population, at least, are getting their news from the Gemini answers, basically. And that some researchers had done some work that showed a kind of preponderance of right-wing talking points within those news answers, which they put down to basically the fact that people are generating right-wing AI slop because it gets lots of clicks and you can make money out of it and so on. So I was kind of thinking about the biases that you were talking about there and wondering about the increase in the, you said, oh, let's just assume that we can use that bias to improve our entailment models, right? The bias that if it's in the text is true. But if we're generating more and more and more training models which have more and more and more falsities in it, that seems kind of on a hiding to nothing, perhaps?
Yes, that's true.
Okay.
I don't know whether to give, I'll answer your question, then Sholem, who knows more about this than I do, will maybe take it up. There's a tremendous danger at the moment that not only human-generated slop, but actually large language model-generated slop will dominate the training data. Clearly, if we just add the output of large language models to the training data regardless, then we are headed down a sort of tunnel of garbage that we'll never get out of again. It's a real problem, and there's no easy solution to it that I know. You can stop using data after 2019, but that's not going to do it. Or you can, it's a hideous problem.
I think the person next to you, David, had a question.
Thank you. My question is about how often ways of getting around the ethical and safety restrictions that are applied to LLMs is to exploit their lack of ability for inference. We can look at the Grok example in order to trick the model to produce stuff that goes against its restrictions. My question is about how we can use entailment to strengthen LLMs to avoid this type of exploitation?
Well, if your entailments are true, if logic will win in the end, I believe. So if you can confine your examinations to logical and even probabilistic logic, then you have a chance of containing these things. But the problem of making large language models proof against jailbreaking manipulation is a very hard problem, and I don't know of any answer to it. And it arises because of the fundamental difference between the processes that human beings, good, bad, and all of them, use in coming up with their own inferences.
Is there any, well, yes, and then the back.
Hello, Professor. Thank you for your amazing, insightful lecture. My question is on the hallucination problem you mentioned for the LLMs. Do you think it's just the retrieval failure or the reasoning failure, or is there like something deeper about the statistical prediction and truth, like are they like structurally incompatible for us to put across in such systems? Thank you.
It is a question of the distribution of the data that they're working on, and the fact that they're built to generate probabilistically, and if the training data that they have been trained on is not enough to bias them towards the veridical answer, they will still come up with an answer. And we all have anecdotes of these things, but there is an industry of looking within the large models to try and find, to try and be able to detect that something is coming, that the machine is coming up with an answer that it has low confidence in. And if you can do that, you can flag that model. You can sort of print it in red or something like that to say that it's been generated by uncertain information and warn the user. But again, it's a problem to which it's very hard to find a secure solution. By the nature of the problem, things are bound to get through.
I think there was a question there. Yes, this gentleman there.
Hi, thanks, Mark. I'm wondering this problem that also David was referring to of staying within language and within the training data. When we do linguistic semantics, of course, one of the things that we are taught and that we teach our students is that there's a interpretation of sentences in a model. There's a model theoretic interpretation, and what you were doing is you're staying within relations within text. And I thought the idea was that at least some people have is to try to provide the LLMs with a model of the world and allow them to induce a real semantics that way. Can you comment on that?
Yeah, I think that is the solution. But the problem is that if you're talking about system 2, if you're talking about real logic, our ability to actually model that world knowledge in a way that can be accessed by the machines is still limited. So it's very difficult to model the real world. The most productive route, I think, is to actually give the models experience in the real world. So if you have a model, if you have a robot, a mobile device of some kind that can not only encode text, but experience the world and bump into things and pick up cues in the visual input that are more like words, general purpose properties of images, perhaps junctions between lines, which in an environment like this give you a great deal of information about spatial relations. That way, you might actually work towards a representation that was not just a System 1 model, but actually had a proper representation of the world of essentially a System 2 kind. And I think that that has always been the goal of artificial intelligence as it was when I was a student. And it's a goal that is still to be achieved.
So I think we have time for one, maybe two more questions. So yes, let's take those two questions there. So yeah. Thank you. Yes.
Thank you. It seems very strange in a talk funded by the Philological Society that you're not mentioning the Oxford English Dictionary and all the other dictionaries that exist and which were built by people who work very hard to try and work out what words mean. And the large language models have gone back to the beginning and scrapped all of that, deliberately ignored it. Is there any possibility, do you think, of building, of actually including the Oxford English Dictionary, et cetera, all the other dictionaries in the database?
Well, you can be quite sure that that text has been used in training these models, along with a lot of other text. The problem that I spend most of my time working on syntax and structural things that resemble the Oxford English Dictionary. But we unfortunately have failed to make those System 2 resources work at the scale that these System 1 devices have been made to work. So unfortunately, all of the marvelous work that you're talking about, that the Philological Society is dedicated to, and that I am dedicated to myself, unfortunately has not been fast enough to come up with workable solutions of the same kind. I believe that they will, and that's why I believe that the future lies with hybrid systems that exploit the strengths of both kinds of models, the logical strength of linguistics and linguistics of all kinds, and the recall strengths of huge models of the other kind.
We have time for one more question, and please, could it be brief?
I will try to make it brief.
Yeah.
In the translation industry, there's oftentimes a combination of NMT and LLM to produce the target text, and then human post-editing on that. Is there an argument or is there precedent for using LLMs and the entailment models together in that hybrid system for the use case of translation, say from Chinese to English or English to Chinese?
Yes, I think that translation is a very good example of a system where it's a disaster unless you post-filter it with a human being who actually understands in the System 2 sense what the meaning is. And I suspect that there will never be there'll never be an end to the need for that kind of monitoring of these things. And we see it in the code area that all of the companies are spending all of their time verifying the draft code that is produced by these things, just as you verify the draft translations that are produced by these simple devices.
Okay, I'd like to thank Mark for a fascinating talk. If you did not get a chance to ask your question or you have an issue you want to pursue, you'll have an opportunity to raise it with Mark at the drinks reception which follows. So please join us. Thank you very much.